There's something pulling. You can't see it. You can't feel it, but it's there. It runs through the walls of your room, through your own body, through the empty space above your bed, and out beyond the ceiling, beyond the sky. It holds entire galaxies together, threading through them like an invisible weight no one has ever touched. We call it dark matter, not because it's sinister, but because we cannot see it, cannot catch it in a detector, cannot hold it the way you'd hold a stone. And here's the strange part. There's far more of this invisible something than there is of everything you've ever seen. Every star, every planet, every grain of sand, all of it together is the smaller half of the story. Most of the universe is made of something we cannot find. And almost nobody thinks about it. Just lie back, if you can, and imagine the lights are off. Your room is dark. The sky outside is darker. And the universe itself, in a way, is in the dark about most of its own contents. You know, a single person lying there with your own memories and worries and half-finished ideas actually know that the universe is missing something in its accounting. Tonight, I want to offer you a strange and gentle idea about what that missing something might be. Very speculative and not something you need to believe. What if dark matter is not a new kind of stuff at all? What if it is the weight of information, of memory, that the universe cannot quite bring itself to erase? Physics tells us that erasing information is not free. Even deleting a single bit, in principle, has an energy price. So simple, it is almost funny. Forgetting has weight. Over the next 2 hours, we are going to walk toward that thought very slowly. We will begin with familiar pictures of stars and galaxies, with the way their motions first revealed the missing mass. Then, step by step, we will drift into ideas about entropy, information, and something like cosmic memory. Some of it is going to be abstract, and all of it is meant to be calm. You do not need to keep up. You do not need to remember every name, every number, every piece of mathematics. This is a story you can fall asleep to, the way someone might read to you at the end of the day, even as underneath the drowsiness, it very quietly rearranges how you think about what reality is made of. So let me tell you how this mystery first walked into the room. Imagine you're looking at a spiral galaxy through a telescope, a slow luminous pinwheel, arms of starlight curling out from a bright center. You see clusters of young blue stars, lanes of dark dust, a faint ghostly disk stretching farther than you'd expect. It looks delicate, as if a strong breath could blow it apart. Now, in principle, it is very simple to ask how fast that pinwheel is turning. You look at the light from stars on one side and the light from stars on the other, and you measure how their colors shift because of motion. A tiny reddening here, a tiny blue tilt there. So simple, it's almost funny. From those shifts you can work out how quickly the stars are orbiting around the center. Think about a solar system. Planets close to the sun move quickly. Farther out, they move more slowly, because gravity weakens with distance. The pull fades, the leash loosens, the outer orbits take their time. By the same idea, in a galaxy, stars far from the center should circle more lazily than stars near the core. That's where Vera Rubin enters the story. In the 1960s and 70s, she spent long nights at observatories patiently collecting the light from spiral galaxies. Not just the bright central regions, but as far out along the disk as the instruments would allow. Point by point, she built what are called rotation curves, graphs of orbital speed versus distance from the center. Here's what we do know. If only the visible stars and gas were providing the gravity, those curves should rise near the center, then fall off, like a hill that slopes back down. Instead, Rubin found that the curves rose and then stayed flat. The outer stars were moving just as fast as the inner ones. In many galaxies, too fast to be safely held by the gravity of everything you could see. By the usual rules, those galaxies should have been flying apart. Rubin's work was not the first hint. A very long time ago, in the 1930s, Fritz Zwicky had looked at entire clusters of galaxies and noticed something similar. The galaxies inside were moving so rapidly that, by visible mass alone, the cluster should not hold together. He proposed there was missing mass binding it all, more than the light was revealing. Slowly, these clues began to rhyme: galaxy clusters moving too fast, spiral galaxies spinning too fast. Later we would even see light from distant galaxies bent and magnified by invisible halos of gravity around closer clusters. Everywhere we looked, orbits were being tightened, paths were being curved by something heavy and unseen. We honestly don't know for certain what that something is. We only know that if you treat it as extra matter spread in a vast halo around each galaxy, the numbers suddenly make sense. The pinwheel holds together, the cluster does not fly apart. In the next step of the story, we'll follow that quiet assumption that there really is extra matter and watch how it reshaped our picture of the entire universe. So now imagine we quietly accept that extra matter really is there, and then use it as a lantern. Light becomes our probe. Let me tell you a simple picture. Far away, a galaxy is shining, its light streaming through space for hundreds of millions of years. On its way to you, that light passes near a massive cluster of galaxies. Space there is not flat, it's gently dimpled by gravity. So the light doesn't travel in a straight line, it curves. Think about looking through a thick piece of old glass in a window. The world on the other side is still there, but the shapes are stretched, doubled, smeared into arcs. In the same way, when light from distant galaxies passes near something heavy, the image you finally see is warped. Astronomers call this gravitational lensing, but the idea itself is so simple it's almost funny. Mass acts like glass. Here's what we do know. If you measure how much those background galaxies are stretched and twisted, you can work backwards. You can reconstruct the invisible glass. You can draw a map of where the mass must be, even if that mass doesn't shine. When people did this for clusters, they found enormous halos of gravity extending far beyond the bright galaxies and hot gas. The visible matter was just the glowing tip of a much larger, dark structure. And then, a very long time ago, in cosmic terms, something dramatic happened that made this picture unavoidable. Two galaxy clusters ran into each other. Today we call the aftermath the bullet cluster, because one clump of hot gas looks like a bullet tearing through the other. The gas is ordinary matter, protons and electrons heated until they glow in X-rays. When the clusters collided, that gas slammed together, slowed down and piled up in the middle like two clouds crashing. But when astronomers mapped the gravity using lensing, the center of mass was not where the glowing gas was. The strongest lensing came from two regions that had passed right through each other, following the galaxies themselves, not the gas. The gravity and the light had separated. That's where the bullet cluster becomes so striking. If all the mass were in normal matter, the center of gravity would sit on the bright X-ray clouds. It doesn't. The numbers only work if most of the mass is in some non-baryonic component, something that barely collides at all and simply sails through, curving space-time and bending light while remaining otherwise invisible. Piece by piece, systems like this have built a quiet consensus. Whatever dark matter is, it behaves like mass in Einstein's equations. It shapes orbits, it sculpts lenses, it neither shines nor absorbs in any familiar way, and yet its fingerprint is written across the sky. But if it walks like mass and bends light like mass does, it'd have to be made of particles in the way we usually imagine, or could the universe be hiding something even stranger in that invisible glass? For a long time, almost everyone working on this puzzle made what felt like the safest move you could make in physics. If something behaves like invisible matter, then surely it must be some new kind of matter. So let me tell you how that idea grew in the late 20th century as those flat galaxy rotation curves and ghostly gravitational lenses piled up. Theorists imagined a new family of particles drifting through the universe, slipping through you and the Earth, the way light slips through a window at night. They gave them names that sound technical but are really very plain: weakly interacting massive particles, or WIMPs, and much lighter whispering particles called axons. Think about what those names are saying: massive, so they gravitate; weakly interacting, so they do not light up or bounce off things very often. You could be surrounded by oceans of them and almost never notice a single splash. If that is true, then every so often one of these particles should bump into an atomic nucleus. Just a tiny tap. So deep underground, under mountains and old mines, people built enormous silent vats of liquid xenon or argon, shielded from cosmic rays, wrapped in sensors, waiting for the faintest flash of light or tiny ripple of charge that would mean something unseen just nudged an atom. At the same time, in machines like the Large Hadron Collider, we smashed known particles together at enormous energies and watched what came out. If a WIMP carried energy away without leaving a track, it would show up as a missing piece in the energy accounting, like money vanishing from carefully balanced books. Here's what we do know. The detectors work, the beams collide, the data streams in. But year after year, as the experiments become more sensitive, as they exclude more and more possible masses and interaction strengths, the clear, repeatable signal of a WIMP or an axion has not appeared. We honestly don't know for certain whether they are simply hiding in some narrow corner of possibility, or whether nature has chosen a different story entirely. There was another, simpler idea, and all of it sounded almost comforting. Maybe dark matter was not exotic at all. Maybe it was just regular objects that do not shine very much. Faint stars, cold planets, dead remnants, black holes wandering through the galactic halo. People call them MACOs, massive compact halo objects, a name so simple it is almost funny. If that were true, then every so often one of these hidden bodies would pass in front of a background star and briefly magnify its light, a tiny gravitational blink. So astronomers watched millions of stars for a very long time, counting these microlensing events the way someone once counted pebbles. They found some, but not nearly enough to add up to the missing mass. That's where the unease slowly grows. When you keep building better nets and catching nothing, you have to ask whether you are fishing in the wrong ocean. If the particles we expected refused to show themselves, could it be that dark matter is not a new kind of stuff at all, but a new kind of question about what the universe is keeping track of? So before we follow that new kind of question, let's do something that the universe itself seems to like doing. We're going to slow down on purpose. You don't need to hold everything in your head at once. You don't need to chase every strange possibility the moment it appears. Instead, let me tell you how this is going to go, like laying out a gentle path before a long evening walk. We'll begin with gravity, but not as an enemy from a textbook, just as the quiet rule that tells stars how to circle a galaxy and tells light how to bend when it passes near something heavy. Galaxy rotation curves, those flat lines that refuse to dip the way they should, will be our first guide. Gravitational lensing, the way distant galaxies are smeared and stretched into arcs, will be our second. From there, we'll turn to information, not passwords or phone numbers, but information as the simple fact that the world could have been one way and is instead another. Here's what we do know: whenever you erase information, even a single bit, there is tiny cost in energy and entropy. That link between memory and heat is going to matter later, even if right now it feels almost too small to care about. Then we'll bring the two together. Some of it is going to be speculative, because we honestly don't know for certain whether gravity might emerge from something deeper, like the way temperature emerges from the jostling of countless invisible molecules. There are proposals where the pull we call gravity is really the universe rearranging information, trying to keep track of what can and cannot happen. To keep all of this from turning into a blur, we're going to follow a single thread through a very large tapestry. Think about a woven cloth hanging in a dark room. You can't see the whole pattern, but you can see one loose strand being tugged from deep inside. In this story, dark matter will be that visible tug, the small motion you can see at the edge of a galaxy, hinting at something woven far inside the fabric of space-time itself. And we'll circle back again and again. Key ideas will return in slightly different clothes, the way a melody repeats in a piece of music. If your mind drifts for a moment, that's fine. The shape of the story will still slowly settle in. Here's the pattern interrupt. Later on, when we look again at those rotation curves and those lensing maps, we will try reading them as something else. Not maps of hidden mass, but maps of where the universe's information might be densest, where its memory is hardest to erase. And all of it will still be grounded in the same simple question. What is the cosmos keeping track of, and why does that bookkeeping have weight? To see what that bookkeeping might mean, you have to look again at something you've known in a vague way for a very long time. We say gravity pulls things down, as if there were invisible strings tugging on every object. But in Einstein's picture, there's no distant pulling. There's only space-time, quietly changing shape. And everything that lives in that space-time, including you, simply follows the easiest possible paths through it, the way a marble rolls along the grooves of a warped table. So the real question is not what is doing the pulling, but what is doing the bending, what tells space-time how to curve in the first place. Here's what we do know. It is not just solid, heavy stuff. It is energy and momentum and pressure and all the restless ways the universe can store and move its content. Physicists give this collection a slightly intimidating name, the stress-energy tensor. But let me tell you, behind the label, the idea is simple, almost so simple it's funny. It is a careful ledger, a bookkeeping device that, at every point in space and time, keeps track of how much energy there is, which way it is flowing, how hard it is pushing. Space-time reads that ledger and responds by curving. Think about what that means. Gravity is not loyal to matter as such. It does not care whether something is made of atoms you can touch or of light you can't hold in your hand. If it carries energy, it counts. If it carries momentum, it leaves a fingerprint in the geometry of the world. Radiation, electromagnetic fields, even the pressure inside a star, all of them weigh in this quiet geometric sense. There's a famous thought experiment that makes this less abstract. Imagine you have a perfectly mirrored box sitting on a scale. At first it is empty, you weigh it. Then you shine light into it and close the lid, so the photons bounce around inside trapped. You weigh the box again, the reading goes up. Not because you added atoms, but because you added energy. The light itself contributes to the gravitational mass. So when astronomers talk about the mass of a galaxy, hidden or not, they are secretly talking about everything in its stress-energy ledger. Cold gas, hot plasma, starlight, dark radiation, if it exists. All of it curves space-time, all of it can hold stars in their orbits and bend the paths of passing beams. Now here is the gentle, unsettling step. If information is never free, if every bit is tied in a deep way to energy and to entropy, then its entries might also appear indirectly in that same ledger. We honestly don't know for certain. But if the universe is running a computation that began at the beginning of time, could its accumulated memory leave a faint gravitational footprint, even when there is no ordinary matter in sight? That's where we start to look at empty space a little more carefully. So let me tell you about someone who quietly changed what it means for the universe to remember. In the 1960s, a physicist named Rolf Landau was thinking about something that on the surface looks almost boring: how computers handle bits. Little zeros and ones, but Landau's idea was that these marks in memory weren't just abstract symbols in a notebook of mathematics. They had to live somewhere, on a magnetic grain, in a transistor, in some tiny physical system sitting in the real world. Think about that for a moment. If a bit has to live in matter, then doing something to the bit means doing something to the matter. You cannot flip a 1 to a 0 by pure thought. Some device has to move, or switch, or release energy. Information, in other words, is not floating above physics. It is made of physics. Landau pushed this further, and this is where his principle appears. He noticed a special moment in any computation, not when you write information, but when you erase it. When you take a memory cell that could be a 0 or a 1 and you force it into a standard reset state. In that act of erasing, the device loses track of which of the two possibilities it used to hold. That loss has a price. Landau showed that erasing a single bit must release at least a tiny, definite amount of energy as heat, an amount proportional to the temperature of the device. 1 bit, 1 minimum heat cost. It is so small it is almost funny, but it is there and it cannot be wished away. Here's what we do know. Every time your computer deletes a file or your phone clears some cache in the background, it is not just tidying up symbols, it is dumping a whisper of heat into the room around you. Every reset of memory, every forced forget is paid for with energy that seeps out into the environment. This is the quiet revolution. If forgetting has an energy cost, then information is tied to thermodynamics. The universe cannot simply erase its records for free. To forget, it must warm something somewhere by some amount. The cosmic ledger we talked about is not only counting particles and light, it is also keeping track of what has been thrown away. And all of it has been going on for a very long time. Stars form and die, atoms collide, quantum events branch, and then get coarse-grained and erased by larger processes. If the universe is continuously processing and discarding information, then over billions of years there is an enormous energetic bill to be paid. Some of it is going to be obvious, like the glow of background radiation. But if the universe cannot delete its memory without leaving a trace of energy behind, could that trace pile up into something we mistake for hidden mass? In the darkness between galaxies, is there a heat cost we have not yet fully counted? To see what that missing heat cost really means, you can shrink the whole universe down to a kitchen table. Imagine a shallow box on the table and a handful of glass marbles. You place them in a perfect pattern, a little crystal lattice you made up. Every marble in a neat row, every gap exactly the same. If someone looked from far away, they could describe the whole scene in just a few words: 10 marbles arranged in a grid. Now you put the lid on, shake the box slowly for a while, and open it again. The marbles are scattered, some touching the walls, some clumped, some alone. From a distance, it is still the same macro picture, 10 marbles in a box. But here's what we do know: there are many more microscopic ways to be jumbled than there are to be perfectly lined up. In the neat case, the marbles have to be in almost exactly one configuration. In the messy case, there are countless possibilities that all look equally random to you. Entropy is a number that tells you how many of those hidden arrangements are compatible with what you see, or, if you like, how much information you are missing about the exact details. You do not know which marble has which tiny scratch, or which one is leaning a little against its neighbor, or which is moving a fraction of a millimeter this way or that. All of that is part of the true microstate. Your eyes and your patience only ever register the macrostate. 10 marbles, roughly spread out, high entropy, a very long time ago. Someone named Claude Shannon looked at a different kind of box. Not a box of marbles, but a box of messages. Let me tell you how he measured surprise. He imagined information as answers to yes-no questions. Each question you ask splits the remaining possibilities in half. 1 bit is the amount of information you get when a single yes-no answer removes half your uncertainty. Think about flipping a fair coin before you look. There are 2 equally likely outcomes. 1 bit of information is exactly what you gain when you finally see the result. More uncertainty means more possible messages and more bits needed to pin down which one you actually received. And that's where thermodynamic entropy and Shannon's information entropy quietly meet. Both are counting possibilities. Both grow when you lose track of fine details and can only say, it's somewhere in this big set of options. The hot gas in a star, the jumbled marbles, the stream of bits on your phone, all of it can be described by how many micro-histories could have produced what you observe. So when we say the entropy of the universe increases, we are also saying that the universe's hidden bookkeeping of microstates is becoming richer and more elaborate over time. The list of ways reality could be consistent with what you and I can see grows longer and longer. If dark matter is tangled up with information, that growing ledger may not be just an abstract idea. It may have weight, so if the ledger is growing, you can imagine the universe itself as a kind of quiet, patient computer. Not a metal box on a desk, humming and heating up. Computer made of stars and vacuum, where every interaction between particles is like a tiny logical operation, clicking over from one possibility to another. Think about 2 atoms colliding in a distant cloud of gas. To you, it is nothing, a small, forgettable event in an empty piece of sky. But at the level of physics, something very precise has happened. Momenta change, quantum states shift, probabilities get updated. The universe has taken in an input and produced an output, and in doing so, it has written a new line in its hidden bookkeeping. Here's what we do know. In both quantum mechanics and relativity, there's a deep suspicion that information is never truly lost. Quantum processes can scramble information so thoroughly that it looks random, and relativity ties information to the fabric of space-time itself. But when you follow the equations carefully, the total content is conserved, transformed, yes, erased. No, that's where Landau comes back in. A very long time ago, he pointed out that erasing 1 bit of information has a minimum energy cost. To truly delete, you have to dump heat into the world. And the universe, being economical in its own strange way, seems to prefer not to pay that bill. Instead of cleanly wiping bits, it disperses them. It lets them leak into more degrees of freedom, into more subtle correlations, into the background hum of fields. So you can picture reality as a universe-sized hard drive. Every star that forms, every black hole that swallows light, every photon that scatters off a dust grain, writes bits into the structure of space-time and the quantum fields that live on it. The pattern of galaxies, the ripples in the cosmic microwave background, even the way time dilates near something massive, all of it is part of this grand ongoing computation, and all of it has to be stored somewhere. Over 13.8 billion years, that is a lot of storage. Every decay, every fusion reaction, every tiny quantum choice contributing another sliver of information to the cosmic archive. Individually, the bits are unimaginably small. Taken together, they might not be so small anymore, which is almost funny given how abstract the idea sounds. We honestly don't know for certain what dark matter is. But if the universe cannot bring itself to forget, if it keeps shuffling information instead of deleting it, you can ask a quiet question. After all this time, could the accumulated weight of that ceaseless information processing be showing up in our equations as something we currently call dark matter? And if that's even close to true, then the missing mass of the cosmos is not just stuff we have not seen yet. It is memory. But if the universe is remembering, what exactly is it remembering, and how would we ever read it? To even ask what the universe might be remembering, you first have to be willing to doubt something so basic that it usually feels untouchable. Not dark matter, gravity. For a very long time, we treated gravity as the most reliable character in the story. Apples fall, planets orbit, galaxies swirl, and the same simple equations seem to describe all of it. If the stars in a galaxy move too fast, you add invisible matter and keep the law. You protect the rule by inventing new stuff. But someone eventually asked a quieter, more unsettling question. What if there's no new stuff? What if the rule itself bends just a little? When you look at the world on the largest scales and the slowest motions, that's where an idea called MOND comes in, modified Newtonian dynamics. The name sounds heavy, but the basic thought is almost disarmingly simple. So simple, it's almost funny. Think about the pull you feel from the Earth right now. It's strong compared to the tiny, delicate accelerations of a star moving slowly around the edge of a galaxy. Mond says that when accelerations become that small, gravity might not keep fading in the way Newton's law predicts. Instead, below a certain threshold, the force becomes slightly stronger than you would expect from the usual formula. If you do that, if you gently tilt the rule instead of adding unseen matter, many galaxy rotation curves suddenly make sense. The outer stars no longer need a huge dark halo to keep them from flying away. The mathematics of the orbits can be fit with almost no dark matter at all. Here's what we do know, though. Mond has trouble when you zoom out even further. Galaxy clusters, with their hot gas and complex motions, still seem to need extra mass. The early universe, as seen in the faint ripples of the cosmic microwave background, does not line up cleanly with Mond's predictions. And while people have built relativistic versions to live alongside Einstein's theory, none of them has become a widely accepted foundation. So some of it is going to be incomplete, and all of it is still very much in progress. Another path takes an even stranger turn. Let me tell you about Eric Verlin's idea of emergent gravity in his picture. Gravity is not a fundamental force at all. It is an entropic effect, something that appears when the information describing the positions of matter changes. When you move matter around, you change how many microscopic states the universe could be in, and that change shows up as what we experience as a pull. In this view, geometry, gravity, and information are woven together from the beginning. Space remembers these proposals are debated, unfinished, and sometimes sharply criticized. We honestly don't know for certain whether any of them is right. But they share a quiet theme. Gravity and information may be more deeply linked than our everyday experience suggests. And if gravity can emerge from information, then the next question almost asks itself, what happens when the universe accumulates more information than its geometry can comfortably hold? There's a strange answer to that question. It begins with a picture on a piece of plastic you've probably held 1,000 times. Think about the little hologram on a credit card. To your eyes, it looks flat, just a thin, shiny patch. But when you tilt it, a three-dimensional image seems to float above the surface. A bird, a globe, a company logo with depth and shadow, all of that volume, all of that apparent space, is encoded in an almost two-dimensional pattern of lines and colors. That simple trick, so simple it's almost funny, is the easiest doorway into what physicists now call the holographic principle. Let me tell you how it arrived. It did not begin with galaxies or dark matter. It began with something much smaller and far more mysterious. Black holes. When someone throws matter into a black hole, You'd think the information about that matter would just disappear. That was the puzzle a very long time ago. Jacob Bekenstein asked a quiet question. If information is physical, should a black hole have an entropy, a measure of how many internal states it could be hiding? Stephen Hawking, following the mathematics of quantum fields near the event horizon, found that black holes radiate and that their entropy is not proportional to their volume, as you might expect from everyday experience. It scales with their surface area, with the area of the event horizon. Here's what we do know. In all our other familiar systems, the number of microscopic arrangements grows with the volume of the region you're looking at. A box of gas, a chunk of metal, your own body, double the volume and you roughly double the room for microscopic details. But for a black hole, the numbers line up with the area of the boundary as if the true bookkeeping of reality lives on the surface. That was shocking. It suggested that the maximum information content of any region of space might also scale with its enclosing area, not its interior. As if the world inside were a kind of projection of data written on a distant screen. If space-time itself is holographic, then the positions and motions of matter, stars, planets, even you, could be encoded on faraway boundaries, cosmic screens surrounding regions of the universe. The bulk of space would be like the floating 3D image on your card, and the real information would live on the edges. Now imagine that information changing when something moves. A star drifts, a galaxy rotates, and the pattern on those invisible screens must update. That means a change in entropy, a reshuffling of microscopic bits. In some of the boldest ideas about emergent gravity, that reshuffling resists. The resistance feels from the inside like a force pulling and curving paths. We call that force gravity. And if gravity itself can arise from the universe's attempt to manage information on its own boundaries, you can already see the next question forming: what happens when those holographic screens are pushed close to their informational limits? When those holographic screens are pushed to their limits, something gentle but important begins to happen. The universe starts to behave as if there's extra gravity, even when you do not see extra matter. To feel what that means, let me tell you about something much simpler than a galaxy. Think about a rubber band lying loose on a table. You stretch it, hold it tense, and then let go. It snaps back. You're used to calling that an elastic force, but you can also tell the story in terms of hidden arrangements. In the stretched state, the long molecules inside the band are lined up and orderly. There are only a few ways for them to be. When the band contracts, those molecules can twist, bend, and wiggle in many more patterns. There are more microscopic configurations available, more ways for the same stuff to be arranged, and in the language of physics, more possible arrangements means higher entropy. The band wants to contract, not because it has a mind, but because there are simply more ways for it to be small than to be stretched. The pull you feel on your fingers is an entropic force. So simple, it is almost funny. Now, take that feeling and move it to the edge of the universe. In Eric Verlinde's picture, you imagine a holographic screen, a kind of imaginary surface that stores information about what is inside. You place a small test mass just in front of it. When you move that mass a tiny distance, you change how many microscopic states are available on the screen. The information content shifts. The entropy changes. If the number of possible states increases when the mass moves closer, there is again a preference for that direction. The universe can realize more internal arrangements if the mass falls inward. That preference shows up in your experience as a pull, a force that looks exactly like gravity. Here's what we do know in this framework. The visible matter in a galaxy does not just curve space. It also changes the bookkeeping of information on these holographic screens. At very large distances where gravity is usually weak, The way this information reorganizes can add an extra emergent pull. From far away you would say calmly and confidently that there must be unseen mass holding the galaxy together. But in Verlinde's emergent gravity, some of it is going to be the universe's information structure, behaving like an entropic rubber band on cosmic scales. We honestly do not know for certain if this is the right story. The mathematics is young, the tests are difficult, and the world has a way of surprising us. But the motif is clear and strangely beautiful. Gravity, in this view, is not a fundamental command written a very long time ago. It is the large-scale reflection of how information is stored, shuffled, and reluctantly forgotten by the universe itself. And if changing information can imitate dark matter's pull, you might wonder what happens when the universe has to remember not just where things are now, but everything that has ever happened. If the universe is carrying this vast, reluctant memory of everything that has ever happened, then it is not just galaxies and black holes that are being held in place by it. It is you right now. Think about the little world inside your hand. The phone you might be watching this on, quietly glowing, asking the surrounding space for timing signals from GPS satellites. Those satellites only work because their clocks and their paths are calculated in a universe where gravity is stable, where the large-scale pull of matter, including the invisible kind, stays predictable over long stretches of time. If dark matter is part of how that memory is organized, then every map that loads, every car that finds its way is leaning on that unseen bookkeeping. The same is true of the building you sleep in, the beams, the concrete, the glass. All of them are made from atoms forged in stars, and all of them are resting in a quiet patch of a galaxy whose overall shape is set by a halo of mass you cannot see. Here's what we do know. The Milky Way does not fly apart, even though its stars are orbiting far, faster than visible. Matter alone can explain. Something, a kind of gravitational scaffolding, holds the spiral together. And your bed, your ceiling, your quiet room are tucked safely inside that structure. Without that extra pull, galaxies might never have settled into the familiar shapes you see in long exposure photographs. They might have formed later more chaotically or not at all in their current patterns. The night sky above you, the simple act of looking up and recognizing a band of light as the Milky Way, depends on this invisible framework. More stars in the right places, more time for stable planetary systems to emerge. And time is the delicate part. If cosmic structure had formed much earlier, the universe would have been a more crowded, more violent place. If it had formed much later, there might not have been enough heavy elements, enough calm orbits, enough long-lived stars for chemistry to slowly explore all its possibilities. Let me tell you, our particular history of stars and planets is balanced on that schedule. A very long time ago, slight differences in density, amplified by dark matter's gravity, began a chain of events that leads eventually to you setting an alarm on your phone, which is almost funny in its simplicity. So when we ask what dark matter is, we are not only asking about distant clusters and abstract equations. We are asking why your present world looks and feels the way it does. Why there is a planet under your feet, a galaxy wrapped around your sky, and a quiet room for your thoughts to echo in. And all of it may be tied to how the universe keeps its memory. We honestly don't know for certain, but that uncertainty is exactly what we are going to walk into next. So before we walk any further into that uncertainty, let me tell you, this is a good moment to step back, to look at the pattern that has been quietly forming while we talked about spinning galaxies and disappearing information. Up to now, we have treated dark matter in the ordinary way, as something like an invisible mass, not glowing, not colliding, but still tugging. We only met it indirectly through motion and light, stars orbiting too fast in the outskirts of galaxies, light from distant galaxies bending around clusters as if there were several times more matter than our telescopes can see. We pictured vast, transparent halos around galaxies, and we listened to the strange story of colliding clusters like the Bullet cluster, where most of the gravity seems to glide straight through the crash. Here's what we do know: whatever is doing that pulling behaves, at least gravitationally, as if it were really there. Real enough to bend paths, to shape structure, to build the cosmic web your world is sitting inside in parallel. We followed a different thread. Information stopped being just an abstract idea and turned into something physical. When you erase a bit on a hard drive, or when a memory in your brain is overwritten, there's a tiny cost in heat, in energy, because the universe refuses to let information disappear for free. That was Landau's quiet remark to physics. Deleting is doing work. So we have two stories, one about gravity answering to energy and mass, one about information secretly being tied to energy whenever you try to get rid of it. Put them side by side and a triangle begins to appear slowly between gravity, information, and what we have been calling dark matter. If that triangle feels slippery, that is completely fine. Some of it is going to be vague on purpose right now. What matters is not that you could pass an exam on the details, but that a certain shape is beginning to live in the background of your mind. A sense that when something moves, when something is remembered, when something is forgotten, the fabric of the universe keeps score. Here's the pattern interrupt. What if dark matter is not matter at all? Not new particles hiding from our detectors, but the way gravity responds to a record that cannot be erased. Think about the universe as a vast, patient notebook, where every interaction leaves a trace in fields and geometry. Call that trace cosmic memory, the idea that the universe might carry, in its large-scale structure and in the fine grain of space-time, a detailed record of its own past. Not a diary you could read line by line, but a stored influence that never quite lets go. In the next sections, we will walk toward this more directly. We will ask what it could mean to treat dark matter as the gravitational shadow of that cosmic memory, rather than a cloud of unseen particles. And all of it will be an invitation not to believe a finished story, but to explore how far this memory-shaped picture of the cosmos can really go. So before we ask the universe to remember everything, it helps to notice how much it is already remembering all the time in very ordinary ways. You can see it in places where the past doesn't just vanish, it condenses into marks. Let me tell you about a cloud chamber. You cool a little box full of alcohol vapor until it is just on the edge of condensing. Invisible particles fly through, carrying charge and energy you cannot see. But along their path, the vapor suddenly turns to tiny droplets hanging in the air like a chalk line on a blackboard. The particle is gone, the trail remains. Each curve and kink in that trail is a memory, a record that something once passed here, with this direction, with that momentum, a very long time ago in particle terms. In a bubble chamber, the same thing happens in liquid. The track becomes a string of bubbles. So simple it is almost funny. You can't see the cause directly, so you read the memory it left behind. The same pattern shows up on much larger scales. Think about a cliff face with its bands of rock, pale limestone, dark shale, a sudden layer of ash. Those layers are geological strata, laid down year after year, flood after flood, eruption after eruption. They are not just rocks. They are a slow archive of climate, sea level, even impacts from space. Tree rings do something similar in wood. Wide, bright rings for good years, narrow, dark rings for hard years. Droughts, fires, insect swarms, all of them leave signatures in the thickness and chemistry of those rings. A forest is a library of weather that no one consciously wrote, but the world wrote anyway. In physics, this idea becomes very explicit. Scattering experiments fire particles at each other and then reconstruct the event from where the fragments land. Radiation backgrounds, like the faint glow of old radioactive elements in rock, tell you about how much time has passed. The abundances of chemical elements in a star, or in the universe as a whole, are records of which nuclear reactions have already happened. Here's what we do know. Once something happens, it tends to leave traces in other things, and the traces do not stop with matter. Space-time itself carries memory. Gravitational waves are ripples from distant collisions, stretching and squeezing space as they pass. They are like vibrations that arrive long after the bell has been struck. The cosmic microwave background is even stranger, a faint bath of microwaves, almost uniform but speckled with tiny temperature patterns. That pattern is a snapshot of the universe when it was about 380,000 years old. It is literally fossil light. If you zoom out further, the large-scale structure of the universe becomes a kind of three-dimensional fossil record. Filaments of galaxies, empty voids, dense clusters, all of it shaped by how matter and energy flowed and clumped over billions of years. You're not just looking at where things are, you're looking at where they have been. And if ordinary matter and space-time already behave like this, quietly keeping score, then the obvious next question is uncomfortable. What happens when we add dark matter to this picture and ask whether the missing mass is really missing at all, or whether it is telling us about a deeper kind of memory we have not yet learned how to read? So if gravity is already a kind of bookkeeping, quietly summing up where things have been, then erasing becomes a dangerous word. Not moving, not copying, erasing. Because in physics, those are not the same thing at all. Think about a simple memory in a computer, a tiny device that can be in two states, which we call 0 and 1. You can shuffle that information around, copy it, swap it with another bit, even run the whole process backward in time in principle. Every distinct beginning leads to a distinct end, and nothing is truly lost. The mathematics is reversible. Erasure is different. Erasure means you take many possible beginnings and force them to share the same ending. Whether the bit was 0 or 1 before, you insist that afterward it will be 0. You're compressing multiple stories into a single final page. And when you do that, the missing detail has to go somewhere because the world does not simply forget. Let me tell you a quieter, more familiar version of that. Imagine you have a deck of cards laid out in a very particular order. Maybe someone spent an afternoon arranging it. You shuffle it thoroughly. Now you have no idea what that order was, but the deck still carries a definite arrangement, in principle. If you filmed every motion of your hands, every swirl of air, you could rewind the tape and reconstruct the beginning. The information is hidden but not gone. Now imagine you burn the deck. The pattern of cards is no longer sitting there on the table. It has dissolved into ash, smoke, heat and light. Yet in the strict language of microscopic laws, even this is not pure destruction. The exact way the paper curled, the way each molecule of smoke drifted away, the spectrum of the glow, all of it is tangled up with the original order. The information has been dispersed into delicate correlations with the environment, spread so thin that for you it might as well have vanished. That is where Landau's idea comes in. Here's what we do know. If you truly reset a memory device, if you force its state into a standard ready position, regardless of what was stored there before, you must increase the entropy of the surroundings. You heat the world, just a little. There's a minimum energy cost for each bit you erase, a tiny toll to pay for the privilege of forgetting. On human scales, that cost is almost laughably small. So simple. It is almost funny. But stretch this process across cosmic time, across every star, every black hole, every quantum event that ever brushed against a horizon, and the bill begins to look less trivial. When information seems to disappear into a black hole or slip beyond a cosmic horizon we can never see past, where does the associated entropy go? If some of it is going to the geometry of space-time itself, could the gravitational imprint of all that hidden bookkeeping be part of what we are calling dark matter? We honestly don't know for certain, but if forgetting has weight, then the next step is to ask how a universe that cannot delete might store its past. So if the universe cannot delete, if forgetting has weight, then you're almost forced to look at the most extreme places where forgetting seems guaranteed. A black hole is that place. Think about a region of space where gravity is so strong that even light, the fastest thing you know, cannot climb back out. There's a boundary around it, a kind of one-way shore called the event horizon. Cross that line, and every path you can take points inward. No return, no escape from the outside. It looks like the ultimate shredder. For a long time, that was the picture. Matter falls in, light falls in, information falls in, and the black hole just sits there silent and dark, described by a few simple numbers, its mass, its spin, its electric charge. So simple, it's almost funny. All the rich detail of what went in seems to vanish behind that smooth horizon. Then in the 1970s, something unexpected happened. Stephen Hawking asked what quantum fields are doing right at the edge of that horizon. And let me tell you, the answer changed how we think about information in the world. Even in empty space, quantum theory says there are tiny fluctuations, pairs of particles that flicker into being and then annihilate. Near the horizon, one member of the pair can fall in while the other escapes. To a distant observer, it looks as if the black hole itself is emitting a faint glow of particles. This is Hawking radiation. Here's what we do know. As the black hole emits this radiation, it loses energy and therefore mass very slowly. Over an immense amount of time, it can evaporate away entirely. A very long time, but not forever. And that's where the information paradox appears. If the black hole disappears into a cloud of perfectly random radiation, what happened to all the information about what fell in? Quantum mechanics insists that information is conserved, that the fine-grained details of a physical system are never truly lost, only rearranged. So does the universe break its own rule at the horizon? Or are we missing something? Many physicists now believe the information is not really lost. It may be encoded in delicate correlations within the Hawking radiation or stored on the horizon itself, almost like the bits on a hard drive. The black hole's surface area turns out to be a measure of its entropy, its information content, hinting that area, not volume, is what really counts. So a black hole, which once looked like a place where information goes to die, becomes a place where information is woven into geometry. Horizons carry entropy, areas carry memory, space-time itself seems to remember. If gravity is already bookkeeping for what black holes cannot forget, then you have to ask a stranger question. What happens when you apply that same idea, not just to one horizon, but to the entire universe? There was a time when we thought gravity only cared about heavy things you could point at, planets, stars, gas. But slowly a different picture emerged. Gravity, in Einstein's mathematics, responds to energy in all its forms. Mass, light, pressure, even the restless jitter of quantum fields. If it carries energy, space-time listens. Now fold in a quieter idea from the world of information. Landau's principle says that erasing a single bit of information has a minimum energy cost. Not doing a calculation, not thinking a great thought, just resetting a memory from something to nothing, heats the environment ever so slightly. It's so simple, it's almost funny. So on one side, gravity reacts to energy. On the other side, information, when truly discarded, demands energy. And then from black holes and quantum theory, you get this strange hint that perhaps the universe never really throws information away at all. It hides it, it scrambles it, but it keeps it. Here's what we do know. Every physical interaction carries information. Which atom hit which photon went where, which quantum state gently rotated into which other state. Think about the universe as a vast, patient accountant, watching every tiny event and quietly writing it down. That's where the metaphor of a cosmic ledger comes in. Imagine that every time two particles scatter, every time a star forms or explodes, an entry goes into the book, not written in ink, but in entropy, in microscopic correlations, in the detailed structure of space-time itself. The books have to balance energy in, energy out, information tracked over a very long time. Those entries add up. 13.8 billion years of stars burning, galaxies colliding, quantum fields fluctuating. If information cannot simply vanish, then the universe must store the record of all of this, somewhere in its geometry, in its horizons, in its fields. And if storing or reshuffling information has an energy cost, then the total cost of maintaining that record is not zero. Spread over cosmic distances, it might look like a smooth, invisible energy density, not localized like a star, not glowing like hot gas, just a quiet background contribution to the gravitational field. Let me tell you the speculative leap. Some of it is going to be wrong, and all of it is an invitation to think. What if a fraction of what we call dark matter is not unseen particles at all, but the gravitational shadow of information bookkeeping, a kind of memory mass arising from the universe's refusal to delete its own history? We honestly don't know for certain. This is not a standard, finished theory. Most physicists still chase new particles, and they might be entirely right. But this changes the question. Instead of only asking what matter is missing, we also ask what information accounting are we overlooking, and that in turn opens the door to a different way of reading the next clues the cosmos gives us. So let me tell you, this is where those quiet, stubborn data points from Vera Rubin come back. You remember the picture, a galaxy spinning in the dark, stars far from the center, moving just as fast as those close in, the rotation curve stretching out flat when, by all our expectations, it should have dipped down. We drew a line on a graph and said, very reasonably, there must be more mass out there. But now imagine reading the same line a little differently. Imagine that what stays flat is not only the distribution of unseen matter, but the distribution of something more abstract, an information field, a kind of invisible bookkeeping, spread through the galaxy that tracks the detailed history of every interaction, every exchange of energy, every tiny gravitational nudge. Think about how we already treat information in physics. Landau's principle tells us that erasing a single bit has a minimum energy cost. Black holes seem to store information on their horizons. Entropy measures not just disorder, but how many hidden ways a system can be arranged. Information is not just an idea in your head, it pushes back on the world. So if the information tied to matter and space-time isn't evenly spread, if some regions carry richer cosmic memory than others, then its gradients could in principle feed into how gravity emerges, not as a new force, but as a subtle reshaping of the familiar one. Here's a thought experiment. Take two rings of stars at the same distance from a galactic center. Same visible mass, same gas, same number of bright points in the telescope. But suppose that in one ring, space-time is carrying far more detailed record of past collisions, close passes, and quantum events. The information density is higher, the entropy structure more intricate in our story. that ring would exert a slightly stronger effective pull, not because there's more stuff, but because there's more memory being maintained. The universe is paying a larger computational cost there, and the geometry we interpret as gravity quietly adjusts. Now stretch that idea to the whole galaxy. The dark halos we infer from flat rotation curves might correspond to extended regions where the universe stores long-lived records of its own past, like a vast low-glow archive. Not a neat disk of stars, but a thick, rounded cloud of information reaching far beyond the visible edge, shaping how everything moves. We honestly don't know for certain. This is a conceptual rereading, not a tested model, and some of it is going to be wrong in detail. But here's what we do know. The rotation curves constrain the gravitational effect, not the underlying ontology. The graph tells you how hard space-time pulls. It does not tell you what, at the deepest level, is doing the pulling. And all of it leaves a quiet question hanging in the dark. If galaxy rotation is already a map, what else in the sky might be secretly tracing the contours of this unseen memory field? So let me tell you, instead of staring at abstract graphs and invisible halos, try a different picture for a moment. Think about the entire universe as a single, gigantic hard drive. Not a shiny metal box on someone's desk, but a quiet, three-dimensional sea, where every tiny region of space is a storage cell, capable of holding a few bits about what has happened there. On an ordinary hard drive, information lives in very simple places. Little magnetic domains on a spinning disk, each one nudged to point this way or that. Or tiny patches of material in a memory chip where a bit is stored as a charge or no charge, a tiny something or nothing that electronics can recognize. When you save a file, you're not putting it into a ghostly cloud. You are flipping trillions of these microscopic switches. The data is the pattern those switches make. And when you read or write that data, you always pay a physical price. The medium is rearranged, magnetic grains flip, charges move, heat is released. Every edit leaves a faint thermodynamic footprint, because information in the end is a physical arrangement of the world. Now stretch that very down-to-earth idea across the cosmos. Instead of magnetic domains, you have quantum fields filling space. Instead of charge on a chip, you have particle states, spins, and momenta. Instead of a flat silicon wafer, you have the curved fabric of space-time itself. In this view, every interaction, every collision of particles, every flash of starlight writes a few new bits into this medium. The universe saves its work. Here's what we do know. When systems become more tangled with each other, when there's more entanglement, more complexity, the information you would need to describe them grows. And that information is not an abstract number floating in a notebook. It is encoded in the actual state of fields and geometry. So a region with a long, complicated history, with many interactions and deep quantum correlations, might need more storage capacity just to keep its own story consistent. If storage has a cost in a laptop, perhaps storage has an energetic cost in space-time. More bits, more effective energy, stronger gravity. It is so simple, it is almost funny. The more the universe remembers, the heavier that memory becomes. Now imagine dark matter halos in this light. Those great invisible cocoons around galaxies would be thickened regions of the cosmic storage medium, places where the universe has had to allocate extra resources to remember billions of years of orbits, collisions, and starlight. Not extra particles hiding in the dark, but extra bookkeeping wrapped around the visible disk. We honestly don't know for certain if reality works this way. But if halos are memory-rich zones, then the next question almost asks itself, how exactly would a universe made of stored histories bend light and move stars differently from one filled with ordinary invisible matter? To even ask that question, you have to turn from poetry back to bookkeeping. because the universe has already written down some very strict numbers in the sky. Those numbers live in the cosmic microwave background, a faint, almost uniform glow left over from a very long time ago, when the universe was only about 380,000 years old. If you could see microwaves with your eyes, the whole world above you would shimmer with it. Not perfectly smooth, but speckled, tiny warm spots, tiny cool spots. Each of those temperature ripples is only a few parts in 100,000. But together they form a precise pattern of bumps and wiggles when you analyze them the way cosmologists do. And here's what we do know: that pattern depends in a very sensitive way on how much dark matter there was, how it moved and how it pulled on ordinary matter. Change the dark matter recipe even a little and the pattern of spots changes too. Think about that as a kind of ancient audit. The early universe rang like a bell, sound waves moving through hot plasma, dark matter, because it does not interact with light, shaped which notes were loud and which were quiet. Today, we measure those notes in the CMB. The relative heights of the peaks in that pattern tell you with almost absurd precision how much invisible gravitating stuff had to be there. Then you let time run. Those same tiny fluctuations grow slowly into galaxies, clusters, and the vast web of structure we see in surveys of hundreds of thousands of galaxies. Where there was a slightly higher density a long time ago, gravity had a head start. Dark matter, whatever it is, deepens those wells and helps pull gas in to form stars, change the properties of that dark component, and the whole growth history of structure changes. So any idea that tries to replace or reinterpret dark matter, including this gentle picture of cosmic memory, has to pass two very strict exams. It must reproduce the CMB pattern, and it must grow the right kind of cosmic web by today. Not roughly, quantitatively, peak by peak, cluster by cluster. Standard cold dark matter models do this remarkably well. You give them simple rules, particles that are massive, slow-moving, and mostly uninterested in anything except gravity. You press play on the equations, the simulated CMB and the simulated galaxy distribution end up looking very much like what our telescopes see. So simple, it is almost funny. That is why, for all their mysteries, these models remain the benchmark. Information-based ideas, by contrast, are still learning how to do this kind of homework. We honestly don't know for certain how to turn stored histories into a precise formula for how space should curve or how fluctuation should grow. And so far, no information as dark matter model has matched the cold dark matter success, number for number. That's where these proposals live for now, at the edge, suggestive, intriguing, but not yet anchored to the sky. The next step, if you keep following this thread, is to ask whether information really can push on space-time the way matter does, and if so, how you would even begin to calculate it. So if information can, in principle, lean on space-time, the next question is almost inevitable. What happens when you actually try to write the numbers down? That's where Eric Valindi walks in. A string theorist by training, he did something quietly radical. He tried to start from entropic and holographic ideas, and from that mist of information derive the familiar pull of gravity that you and I experience, and then compare it to real galaxies. Not just as poetry, as equations. In Verlinde's picture, the universe is not filled with a static stage of space, but with an elastic, information-bearing medium. When you put ordinary matter in that medium, it changes the bookkeeping of information, and that change shows up as an extra emergent pull. No invisible particles added by hand. Just a new term in the way space-time responds to stored information. Let me tell you how that plays out when you look at a spiral galaxy. You take the visible stars and gas, you feed their distribution into Verlinde's emergent gravity formula, and you ask a very simple question: how fast should the outer stars be moving in the usual story? You need a large halo of dark matter to keep those rotation curves flat. In his framework, some of that extra pull appears automatically from the way information is encoded on cosmic horizons. And in a surprising number of cases, especially for certain isolated galaxies, the curves come out close. Sometimes eerily close. You get rotation speeds that stay almost constant with radius without putting in a single dark matter particle. It is so simple, it is almost funny, because the only inputs are the visible mass and a few universal constants. You can feel for a moment the appeal of an idea where gravity itself remembers. But then you lift your eyes from individual galaxies to the wider sky, clusters of galaxies with their hot X-ray gas, gravitational lensing maps that show mass-bending light into arcs, the delicate pattern of temperature ripples in the cosmic microwave background. Here's what we do know: the standard cold dark matter picture with actual particles threads its way through all of these observations with remarkable consistency. Emergent gravity in its current form struggles. The fits to clusters are often off, the lensing predictions are under active debate, and the cosmological story is, at best, incomplete. We honestly don't know for certain whether Verlindi's framework is a stepping stone, a side road, or a dead end. Some of it is going to be refined, some of it may quietly fade. But it is a clear example of information-based gravity ideas finally touching real data, being forced to answer to telescopes instead of just blackboards. And all of it teaches a quiet lesson. Whatever dark matter is, particles, memory, or something stranger, our measurements fence in the possibilities. Think about that fence as we go on, because the next twist in the story will push this information as memory idea into an even harsher observational spotlight. So if measurements fence in the possibilities, there's a strange question waiting right at that fence. What if information itself is leaning on the fence posts, pulling space-time into shape? To see why anyone would even say that, let me tell you about something called entanglement, entropy. You can think of it as a careful way of counting how deeply two regions of the quantum world are intertwined. Not just whether they touch, but how much their possible futures are braided together. Imagine you take the universe and draw an invisible line through it. On one side you have here, on the other side you have there. Entanglement, entropy, is a number that tells you how much quantum information is shared across that boundary. And here's the quiet surprise: in many situations that number does not scale with the volume of space, but with the area of the surface between the two sides. A thin skin, not the whole interior, that simple fact, so simple it is almost funny, echoes something we met a very long time ago with black holes. Their entropy, their information content, also seems to live on the surface, on the horizon, not in the bulk. Area, not volume. It is as if nature keeps whispering that boundaries matter more than we first thought. Now, in some of our best theoretical laboratories, this whisper becomes a shout. In models with names like ADS-CFT, physicists have found that you can, in principle, reconstruct the geometry of a curved space-time just from patterns of entanglement in a lower dimensional quantum system living on its boundary. The shape of space inside is encoded in who is entangled with whom on the edge. In that picture, information is not simply sitting in space-time like books on a shelf. It is helping to build the shelves. The network of quantum correlations, the way information is arranged, actually tells space-time how to curve and connect. Here's what we do know in these frameworks: geometry and information are two faces of the same underlying structure. If that is even partly true in our universe, then you can take a gentle step further. Think about what happens if you change the information structure. If you rearrange entanglement or add more of it, you might subtly change the curvature of space-time itself. From far away, that change in curvature would look exactly like extra mass or extra energy hiding in the dark. Something that bends light, speeds up galaxy rotation, and never shows up as particles in a detector. We honestly do not know for certain whether this elegant story actually plays out in the real cosmos. Some of it is going to be beautiful mathematics on a blackboard, and some of it may never leave the realm of speculation. But that's where the frontier is right now, testing whether information, entropy, and entanglement can genuinely stand in for invisible matter. And all of it leads to a sharper question we will have to face next. If the universe is remembering something in its geometry, what kind of memory would be big enough to weigh down entire galaxies? So before we ask what kind of memory could weigh down galaxies, it helps to pause and look at the two pictures we've been slowly building. Here's what we do know, however you describe it. Something is tugging on stars and bending light. Spiral galaxies spin with flat rotation curves, as if wrapped in invisible halos. Clusters like the Bullet cluster show gravity in one place, and most of the glowing gas in another. On the largest scales, the pattern of galaxies in the universe only makes sense if there's extra gravity in the background. In the standard story, that extra gravity comes from a new kind of matter. You imagine some cold, heavy particles drifting through you right now, barely interacting, adding mass without light. People give them names like WIMPs or axions, and then design careful experiments deep underground, waiting for a tiny collision in a detector. It is a very down-to-earth idea. More pull means more stuff. In the alternative story we're exploring, you keep the same observations, but you let the explanation lean in a different direction. Instead of asking what particles are missing, you ask what information is the universe already carrying. You look at entropy, at the way horizons store bits, at how space-time geometry seems to know about quantum entanglement, and you wonder whether the extra pull is not from extra particles, but from the way information and geometry refuse to come apart. Think about that contrast for a moment on one side. New matter. On the other side, new bookkeeping. Both are trying to account for the same galaxy rotations, the same lensing arcs, the same cluster dynamics and cosmological patterns that have been patiently measured over time. You don't have to choose a favorite, not yet. You can hold them like two overlapping transparencies, one where the blank regions are filled with invisible particles, one where the blank regions are filled with invisible bits of memory woven into space-time. When you slide them together, the bright spots line up in the same places because they are both trying to describe the same world. And we honestly don't know for certain which transparency, if either, is the final one. Some of it is going to be settled by experiments that never see a single dark particle hit a detector, or by new measurements of how galaxies move at the edges. Some of it may come from ideas that have not been written down yet. Here is the quiet shift that might be happening in you as you listen. A very long time ago, stuff meant stones, bones, water, fire. Then it grew to include atoms, fields, and dark matter halos. Now the idea is stretching again, making room for the thought that memory and information are not just mental shadows, but physical, weight-bearing parts of the universe. And if that is even partly true, then asking what dark matter is becomes the same as asking what the universe is remembering and why it can't quite bring itself to forget. If the universe can remember, even in some strange gravitational way, then you already carry a tiny model of that process inside your skull. Think about the thing doing the thinking right now. Your brain is not a cold, silent calculator. It is a warm, wet network of about 80 billion neurons, each one branching into thousands of delicate fibers, all bathed in salty fluid and electrical whispers. With every new experience, some of those connections strengthen, some weaken, some new ones grow, some old ones are pruned away. The wiring diagram is never finished. It is rewritten in real time as memories form, fade and recombine. When you remember something as simple as the way home, you're not opening a little filing cabinet in your head. You are reactivating a pattern, a particular dance of signals across a particular landscape of connections. If those connections change, the memory changes. If enough of them are lost, the memory is gone. And all of that takes energy. Here's what we do know. Your brain is only a few % of your body's weight, but it quietly claims a large share of the energy budget. Glucose and oxygen are ferried in with every heartbeat. Chemical batteries inside each neuron charge and discharge. Tiny pumps in the cell membranes move ions against their gradients, and in the process they leak heat into the surrounding tissue. Remembering is not free. Forgetting is not free either. There's a metabolic bill for every adjustment of a synapse. It is so simple. It is almost funny to store a childhood afternoon. Your body has to burn sugar. Crucially, that afternoon is not stored in one place. There's no grandmother cell with your entire past engraved on it. The color of the sky, the sound of someone's voice, the feeling of grass under your hands, they are scattered across many regions, encoded in overlapping patterns of activity. Destroy one neuron, and the memory usually survives. Destroy the pattern. And it does not, in that sense, a memory in your head is already like information in a field, not a single object, but a structured state spread out over space and time. Let me tell you one way to look at this. The large-scale structure of the universe, the web of galaxies and dark matter halos, could be doing something similar on a scale almost too large to imagine. Just as the particular shape of your neural network quietly encodes your personal past, the particular arrangement of mass and curvature might quietly encode the universe's cosmic past. We honestly don't know for certain whether dark matter is a particle, a field, or something stranger. But if you can accept that your own memories have a physical footprint you could, in principle, measure with instruments, then it is not such a stretch to imagine memory leaving a gravitational footprint as well. And if that is even possible, then the next question is unavoidable. How much does 13.8 billion years of remembering actually weigh? If memory has weight, even in this very gentle metaphorical sense, then you can ask a new question: does it pile up in some places more than others? Think about the universe not as an empty stage, but as a long, slow computation that has been running since the beginning. Some regions barely do anything. A thin gas cloud drifting between galaxies changes only a little from 1 billion years to the next. Other regions are busy, wildly busy. Galaxies are where the action is. Gas falls in, it cools, collapses, and ignites as stars. Those stars fuse light elements into heavier ones, then explode as supernovae, throwing shockwaves through their surroundings. Black holes grow, swallowing matter and stirring space-time around them. Jets of particles and light punch out through the galactic atmosphere. All of that is processing. All of it is the universe taking in a previous state and writing a new line in the cosmic ledger. If there really is such a thing as memory density, you would expect it to be higher where more has happened and where events are more entangled with one another. A galaxy is not just a collection of stars, it is a history machine. Every orbit, every collision, every burst of radiation is one more entry in a record that, in this picture, the universe refuses to erase. Now imagine the space around the bright disk of a galaxy, the region astronomers already call the halo. It is not truly empty, it is filled with tenuous gas, drifting stars, small satellite galaxies, and invisible fields tying everything together. This is where infalling matter is slowed, shocked, mixed, and gradually fed inward. It is where past interactions and future ones overlap. in our thought experiment, that halo becomes more than a place where matter passes through. It becomes the shell where memory is stored most efficiently. Not as a neat stack of files, of course, but as subtle, persistent structure in fields and in the geometry of space-time itself. The inner galaxy does the intense processing. The surrounding halo slowly accumulates the long-term record. If memory really did curve space-time the way energy does, that would be exactly the kind of region where you might expect an extended, roughly spherical enhancement in effective energy density. Something that does not glow, but that adds extra gravity. Something that holds stars in their fast orbits and bends light from distant galaxies, the way we actually see dark matter halos behaving. Here's what we do know. This is not a tested model. We honestly don't know for certain that any of this is how the world works. But as a picture, it gives you a way to visualize what memory clustering might mean physically, instead of as a loose metaphor that evaporates when you look too closely. And if memory can cluster, if it can flow and pool and form invisible halos around galaxies, then there is a deeper question hiding underneath, waiting for us in the dark. What decides where the universe chooses to remember and where it allows itself to forget? If the universe is choosing where to remember and where to forget, then the next quiet question is almost unavoidable. How would you tell the difference between a memory and a particle? In ordinary dark matter stories, the answer is very down to earth. You imagine some new kind of particle with mass, with a way of drifting through space, maybe with a tiny tendency to bump into itself or to annihilate with its partner and release a flash of energy. From those simple ingredients, you write down equations, and those equations tell you what galaxies and clusters should look like. Here's what we do know. If dark matter is made of particles, then their collective behavior is not arbitrary. They should form halos with particular shapes. They should clump on small scales in a certain pattern, and in some models they should occasionally collide with each other, or annihilate and give off very specific signals. Not dramatic explosions, just a faint statistical glow. So people go looking, they point gamma-ray telescopes at the center of our galaxy, where dark matter density should be highest. They stare at tiny dwarf galaxies, dim companions of the Milky Way that seem to be almost pure dark matter by mass. If particles are annihilating, you expect a mist of gamma rays or other products emerging from those places like steam from a kettle, and yet so far the sky is quiet. There are hints and bumps and debates, but no clear universal line that says, this is it. In a strange way, the absence of that line slowly squeezes the space of allowed particle ideas. Some of it is going to be ruled out entirely if the silence continues. Think about what that silence might mean if the stuff is not stuff at all, but information structure. If the extra gravity comes from how space-time stores and processes the record of past events, then you would not expect little flashes of annihilation. You would expect relationships, tight, maybe slightly unusual relationships between the visible matter you can see and the invisible pull you infer. That is where galaxy rotation curves become more than just pretty plots. You can measure how stars orbit at different distances from the center, and compare that to how much starlight and gas you see. You can map gravitational lensing, the way background galaxies are stretched and sheared, and compare that to the luminous matter doing the stretching. Across big clusters, quiet dwarfs, messy interacting systems. If dark matter is particulate, the statistics of those curves and lensing profiles should follow one family of patterns. If it is some emergent memory effect, the patterns might be subtly different, perhaps more tightly tied to the distribution and history of ordinary matter than particle models expect. The differences might be small, but with enough precision and enough galaxies, small can become decisive. Any serious memory-based theory has to lean into that. It has to say very clearly, in this kind of galaxy, you will see this rotation shape. In this kind of cluster, you will measure this lensing strength. And if you do not, the idea is wrong. We honestly don't know for certain which way the data will fall, but the universe is keeping the score for us very patiently. And all of it is written in motions and light, waiting to be read more carefully in the sections to come. So before we follow those motions and that light any further, let me tell you it's worth pausing on a quieter question. Not what is dark matter made of, but what does it even mean to say that something is real in physics? When a physicist writes dark matter in an equation, are they naming a thing out there in the world, or are they really just leaving a blank space, a careful placeholder that says something is missing here? A missing weight in the cosmic balance, a missing term that makes the numbers line up. Think about how many ideas in physics started that way. Fields were once just mathematical decorations on the page, helpful ways to keep track of how a force might vary from place to place. Electric and magnetic fields were invisible bookkeeping devices long before anyone spoke about them, as if they flowed through the room you're in right now. Over time, as experiments piled up, the language shifted. The field became not only a calculation, but a part of what we calmly call reality. The same story plays out with particles. At first they arrive as symbols in equations, little dots in diagrams that make the mathematics behave. Only later do we build machines, see tracks in detectors, measure energies, and decide that these symbols deserve promotion from useful fiction to thing the universe actually contains. There's no sharp day when that promotion happens. It creeps in slowly as confidence grows. Information lives in this borderland too. On one level, it is just a way of describing patterns in matter, the way ink sits on a page, the way atoms arrange in a memory chip, the way numbers line up in a table. But here's what we do know. If you erase information, you pay an energy cost. There's a minimum heat that must be released when a bit is wiped, a tiny thermodynamic bill that cannot be avoided. So simple, it's almost funny. Even forgetting has a price. That energetic price suggests that information is not only in our minds, it is woven into the physical bookkeeping of the universe itself. Not a ghost, but not quite a rock either. Something in between, a structure that rides on matter and energy, yet has its own rules. If you let dark matter live in that same in-between place as memory rather than stuff, the language changes in an interesting way. We stop picturing bags of missing particles and instead picture missing structure, missing records, missing relationships that ought to be there if the universe keeps perfect track of its own past. The gravity we see would then be tugging not only on objects but on the way those objects are arranged and remembered across space and time. We honestly don't know for certain whether that picture is right. Some of it is going to be metaphor, some of it may turn out to be mathematics, and all of it is allowed to remain open for now, like softly glowing lanterns at the edge of the path. In the next part of our journey, we'll walk a little closer to one of those lanterns and ask what it would mean in detail for the universe to be a patient archivist of its own history. There's a strange asymmetry in your own mind that you live with every day. So familiar, you almost never notice it. You remember yesterday, you do not remember tomorrow. Physics has a name for that lopsided feeling. We call it the arrow of time. And here's what we do know, that arrow is tied very deeply to something called entropy, the measure of how many microscopic ways the world can be arranged while still looking the same to you from far away. Think about a drop of perfume in a quiet room. At the beginning, every molecule is huddled together in one corner of space in a very special, very organized pattern. Wait a while, and the scent spreads slowly until it fills the room. You could, in principle, write down numbers for the position and motion of every molecule, but in practice they have been scrambled into countless different configurations. The air now carries a record. It remembers that a little while ago there was perfume in that room, because there's no easy way to put all those molecules back. You almost never see the scent undiffuse itself and leap obediently back into the bottle. That one-way scrambling from simple beginnings to complicated mixtures is entropy increasing. Every time ice melts, every time a star burns its fuel, every time your brain forms a memory, microscopic details are being pushed out into the environment like ripples on a pond that never quite come back. The universe is, in a quiet way, writing. Let me tell you, this is one of the most haunting ideas in modern physics. The present is not just a moment. It is a palimpsest, a layered page, the positions of planets, the temperature of the cosmic background light, the chemical elements in your blood. All of it carries traces of earlier states, like faint handwriting that never fully fades. But the past does not carry traces of the future in the same way. Yesterday's air does not already encode tomorrow's thunderstorm. The past feels heavy because it is encoded in countless correlations and structures. Broken cups, eroded mountains, worn books, tired stars. The future, by comparison, is still light because many of those correlations have not yet been written. You can think about the entire cosmos as a gigantic archive whose shelves are always filling and never cleared. Entropy is not just disorder. It is the weight of all the ways the universe has allowed its information to spread out, to be preserved in ever more diffuse, inaccessible forms. And now comes the speculative twist. If information has a physical cost, if every bit of erased detail leaves some energetic scar on space-time, then the universe's growing memory could in principle have gravity. We honestly don't know for certain, but one wild possibility is that what we call dark matter is the gravitational echo of this one-way accumulation of records, the extra weight of a universe that cannot go back to a simpler state. In the next step of our journey, we'll ask how far you can push that idea before it breaks, and whether the missing mass of the cosmos could really be the shadow of its own history. To see how far we can push this, you have to go back to the very beginning, not to stars or galaxies or even atoms earlier than that. A very long time ago, the universe was hot, dense, and astonishingly smooth. Everywhere you looked, in any direction, you would have seen almost the same glowing fog of particles and light, with only the tiniest ripples in temperature and density. Those ripples are still there, frozen into the cosmic microwave background as faint mottled patterns in a sky of almost perfect uniformity. Think about how strange that is. Today the universe is full of structure. Galaxies, clusters, filaments, vast empty voids. But back then, everything was nearly the same everywhere, like a perfectly mixed soup with just a few grains of spice. Here's what we do know from the point of view of gravity, that early state had very low entropy, not because it was simple in every way, but because matter was spread out so evenly that there were very few ways for it to be different. A smooth mass distribution has far fewer possible gravitational arrangements than one where matter is broken into stars, black holes, and tangled webs of galaxies. As time passed and the universe expanded and cooled, those tiny ripples in the microwave background grew. Ripples that were just a little denser, pulled in more matter. Clouds collapsed, stars ignited, galaxies assembled. Gravitational entropy increased as the number of possible configurations exploded. Smoothness gave way to clumpiness, and clumpiness is where history can hide. If space-time keeps a kind of memory, then this is when the record-keeping accelerates. Each collapsing cloud, each orbiting pair of stars, each galaxy merger is a specific, irreversible choice out of many possibilities. And all of it in this picture writes more detailed records into the geometry of the universe itself, deepening the gravitational imprint of what has actually happened. Now imagine tying that to dark matter. In the very early universe, when everything was almost uniform, the extra weight of memory would have been small, because there simply had not been much structure or many irreversible events. Yet, as structures formed and interactions accumulated, the effective contribution of this memory could grow, not as a new ingredient suddenly appearing, but as a quiet thickening of space-time's accounting books. So simple, it's almost funny, more structure, more memory, more apparent mass. But standard cosmology is a demanding bookkeeper. In our best models, dark matter is already there very early, shaping those first tiny ripples, helping them grow into galaxies. Any memory-based idea has to reproduce that behavior, to look from a distance almost exactly like ordinary dark matter, even when the universe was just a glowing fog. We honestly don't know for certain whether that is possible. That's where the next step takes us, into the detailed numbers of structure formation, where we'll see whether a universe made of memory can really grow the worlds we see today, or whether the idea falls apart under its own history. So if the idea doesn't fall apart under its own history, what would it have to grow into? Not just a picture, not just a metaphor, but an actual framework, written in the same hard, quiet language that we use for gravity and light. In other words, if the universe really remembers, we would need to say what exactly is being remembered. Let me tell you how that might begin. Someone would have to take this soft phrase, cosmic memory, and turn it into numbers. Not poetic numbers, but mathematical ones. You could imagine a field spread through space-time, a kind of information density, telling you how much past experience is stored in each tiny region. Or you might tie it to something we already know how to calculate, like entanglement, entropy, which measures how deeply different parts of the quantum world are linked. The rule would be simple to state, almost so simple it's almost funny, more history, more memory. Once you have a memory field, it cannot just sit there. It has to talk to the geometry of space-time itself. Einstein's equations already say that energy and pressure tell space-time how to curve, and curvature tells matter how to move. A memory-based theory would quietly add one more voice to that conversation. The stored information in a region, its accumulated record of what has happened there, would slightly shift the curvature as if the past were leaning on the present. That is where the mathematics stops being a story and starts being a set of coupled equations. But here's what we do know from experience with physics. Any new framework has to be polite. It must reduce, in the right limits, to the theories that already work. So if you zoom out in time and space, or look at eras when the universe was young and smooth, the extra memory terms would have to fade away, leaving you with ordinary general relativity plus something that looks to a cosmologist exactly like cold dark matter. Galaxies would still form. The bullet cluster would still separate its gas from its main gravitational mass. From a distance, nothing would seem to have changed. Up close, though, the universe might whisper. Tiny adjustments to how structures grow, slight shifts in the way light is bent around galaxies, delicate fingerprints in gravitational lensing maps that future surveys could look for. Think about long baseline observations years apart, watching the same cluster slowly evolve. A memory-driven model might predict a pattern of changes that no simple particle halo could mimic. We honestly don't know for certain whether nature is that talkative, but the predictions would be on the table. And all of it would take time, decades probably. Some of it is going to be wild guesswork at the beginning, toy models written on whiteboards late at night, followed by slow, careful consistency checks. Does the memory field respect the basic rules of thermodynamics? Does it keep causality intact? Can it be simulated without falling apart numerically? Only after that long, patient work could we ask the sharper question, not just is this beautiful, but is this our world? And that in turn sets up the next step, where we stop sketching and start testing whether a remembering universe can survive contact with real data. So why bother with any of this? Why spend time on an idea that might never leave the whiteboard? An idea like dark matter as memory that may turn out to be completely wrong. Let me tell you, this is not a bug in physics. This is how the game is played. Most speculative ideas fail. They fade quietly when the numbers refuse to cooperate. But in failing, they leave something behind. Clearer questions, sharper definitions, new ways to look at the same old sky. Think about the ether. A very long time ago, people were convinced that light needed a medium to travel through, the way sound needs air. So they imagined an invisible substance filling all of space, the luminiferous ether. It was everywhere and nowhere. So simple it is almost funny. Experiments were designed to catch the Earth moving through this ether. They failed. And in that failure, Einstein found room to say, maybe there is no ether at all. Maybe the speed of light is just built into the structure of reality. The same thing happened closer to the atom. You had little planetary systems, electrons whirling around a tiny sun. It was beautiful and wrong. Those early models could not explain spectra or stability, but they trained people to ask better questions, to measure more carefully, to accept that the world of the very small does not behave like tiny clockwork. Out of those wrong pictures came quantum mechanics, and with it the modern mathematics of energy and information. So when we imagine dark matter as memory, we are not just daydreaming. We are forcing ourselves to say very precisely what we mean by information. Is it just numbers on a hard drive, or is it any stable pattern that could in principle be read out by someone somewhere? Here's what we do know. Erasing information has a physical cost. It heats things up, it changes entropy. If the universe has been processing and erasing information for billions of years, where is that cost recorded? Where is the bill? Some of it is going to be wrong. Maybe all of it. Discipline means we do not get to keep an idea just because it feels deep or poetic. We have to let the data answer. Does this memory picture reproduce galaxy rotation curves? Does it mimic the lensing we see in clusters? Can it stand next to the bullet cluster and not fall apart? If not, we trim it or we throw it away and we try again. And all of it, even the failures, trains your intuition. By holding these pictures in your mind, you are quietly rehearsing the same moves working physicists use every day. Imagine, formalize, confront reality, revise. You become part of the long conversation. In the next section, we will lean a little harder into that conversation and ask what a remembering universe would actually feel like from the inside if you could somehow live inside its memory. So if you could live inside the universe's memory, you might start to wonder how it behaves when things collide. Because there's a place in the sky where that question is not poetic at all, but painfully concrete. It's called the bullet cluster. Let me tell you what you're looking at when astronomers point their instruments there. Two galaxy clusters, each one a city of hundreds of galaxies, have passed through one another, a bit like two ghostly clouds. The ordinary matter, the gas between the galaxies, smashed together and heated up, glowing in X-rays. But the main pull of gravity, mapped by the way it bends background light, ended up displaced from that glowing gas. The mass went one way, the brightest matter stayed behind. In the usual dark matter picture, this is almost reassuring. You say dark matter is made of some new kind of particle. It barely notices other matter. So when the clusters collide, their dark halos slide through each other with hardly any friction. The galaxies, which are mostly empty space, also pass through. The gas, however, slams together, slows down, and lingers in the middle. So the center of gravity follows the collisionless pieces, not the sticky gas. It's so simple, it's almost funny how neatly that story fits the image. But if you try to think about dark matter as memory instead of matter, you have to pause here. How could a memory field know to follow the galaxies and not the gas? Could the universe's record be more tightly attached to deep gravitational wells and long-lived structures than to the collisional stuff drifting between them? Here's what we do know: galaxies and their dark halos are stable, persistent patterns in space-time. The hot gas is more like weather. If cosmic memory is stored wherever gravity has carved out a durable configuration, then the weight of that memory might travel with the collisionless skeleton of the cluster, not with the glowing fog. During a merger, the galaxies and their invisible wells move ahead, and the gas is left to shock and stall. The memory in that picture runs ahead of the light. That's where the mathematics would have to do real work. You'd need equations saying how much memory attaches to a given gravitational potential, how it moves, how it lenses light. Some of it is going to be very close to what people already write down for particle dark matter, and some of it would have to be genuinely new. We honestly don't know for certain whether such a memory-based model can ever match the bullet cluster. Right now, that system remains one of the strongest arguments that there is some non-baryonic dark component out there, whether it is made of particles or of something even stranger. But if the bullet cluster is the universe spelling out a message in slow motion, the next question is unsettling. What exactly is being written down, and could that cosmic record ever be read from the inside? If the bullet cluster is a message, then gravitational lensing is how we learn to read its handwriting. When light from a distant galaxy passes near something massive, it does not travel in a straight line. Space itself is curved, and the light simply follows the curve. So when astronomers talk about gravitational lensing, what they are really doing is measuring how space-time has been bent along the entire path of that light, adding up, in a quiet way, the total gravitational effect of everything it has passed. Not just at one point, all along the way. In the usual picture, that means lensing maps are maps of mass. Stars, gas, dark halos, all thrown together into one integrated fingerprint of curvature. But let me tell you an alternative reading. If the information structure of the universe contributes to curvature, even slightly, then those same lensing maps become something richer. They turn into maps of where matter is and where memory is. Think about that for a moment. A fuzzy blue arc in a Hubble image stretched around a cluster would not only be telling you how many trillions of solar masses sit in that region, it would also, in this more speculative view, be whispering how much irreversible history has happened there, how much has been written into the fabric of space-time and never quite erased. Here's what we do know. When teams reconstruct a cluster's mass from lensing, they compare it to the visible galaxies and to the hot gas seen in X-rays. The difference between those is where dark matter usually lives. In our information-based story, you could imagine a new kind of survey layered on top of that. You would still make the lensing map. You would still count the galaxies. But then you would ask a new question: where is the extra curvature strongest, and how does it line up with the region's interaction history? You might look at a cluster with a long record of mergers, where smaller systems have fallen in again and again, stirring the gas, shocking the plasma, turning gravitational energy into heat and radiation. You might compare it to a quieter cluster of similar visible mass, one that has simply coasted through cosmic time. If memory plays any role, even a tiny one, regions with more complicated violent pasts might show subtle differences in their lensing patterns, tiny mismatches between mass and light that do not follow the usual rules. We honestly don't know for certain whether anything like that is there. Current data were never designed or analyzed to look for correlations between extra curvature and messy history. But that's where the next generation of surveys comes in, with high-precision lensing from telescopes like Euclid and the Rubin Observatory. Someone could, in principle, start to ask whether space-time seems to remember. And if it does, even faintly, then the universe has given us a way to read its diary from the outside. The harder question is whether you could ever open it from the inside, and all of it leads us straight into the mathematics of information itself. So let me tell you a quiet, strange idea. There was never a moment when the universe pressed delete, not once. Not on anything that ever happened. If dark matter is, in some deep way, the weight of information that cannot be erased, then you are not just moving through empty space tonight. You are moving through a medium that remembers not as a diary you could open and read, but as a pattern in the way space-time bends and balances its own accounts. Think about an ordinary evening in your life. You boil water for tea, you check your phone, you turn off a light. Each of those tiny actions shuffles energy, flips quantum states, rearranges particles. According to the mathematics of information, none of those changes can be completely undone. There's always some trace, some microscopic difference in the world that says this happened and not something else. In a remembering universe, every moment of your experience leaves a faint, diffuse fingerprint on the cosmic microstate. Not a photograph with your name on it, not a file in some celestial archive, but a contribution to the overall pattern that exists now and will echo in transformed ways for a very long time. Your life becomes part of the boundary conditions of everything that follows. Here's what we do know. Physics already ties information to reality in a very literal way. Erasing bits costs energy, entropy measures, missing information. Black holes seem to store what falls in on their horizons. So the idea that the cosmos keeps the books on its own history is not pure poetry. It is an extrapolation of mathematics we already used to describe heat, light, and time. But we honestly don't know for certain whether dark matter is part of that bookkeeping. Even if it were, it would not mean personal immortality. No future astronomer will be able to dial up a crisp replay of your Tuesday afternoon. Any record would be scrambled beyond recognition, mixed with the records of countless stars, galaxies, and forgotten events. And yet there's something gently comforting in the thought that nothing is entirely thrown away. That when you help someone or speak a kind word or simply notice the world for a second longer before you fall asleep, the universe does not revert to the version where that never occurred. The timeline with you in it is the one that actually exists. It has weight. Literally, perhaps seeing dark matter as memory turns the cosmos from a cold warehouse of invisible stuff into a slow, unfolding narrative written in the language of physics. The missing mass becomes the accumulated cost of having a history at all. More story means more information means more gravitational pull. So simple, it's almost funny. Some of it is going to be speculation. And all of it is, in the end, a way of holding the mystery without pretending we have the final answer. Whether or not the dark universe is truly made of memory, you can let this picture sit beside you like a quiet companion. Because once you start to see gravity as the shadow of information, the next question is unavoidable. If the universe remembers, what exactly is it trying to compute? So let me pull the thread gently before we follow it any further. We began with something very concrete. Vera Rubin watching galaxies turn, expecting the outer stars to slow down and drift lazily around the edge, and instead finding flat rotation curves that refuse to fall. Then the bullet cluster, two clusters of galaxies passing through each other, normal matter in the form of hot gas lagging behind, while the main gravitational pull seemed to march on ahead, invisible yet undeniable. From there you walk through a world where gravity is not just a force but a kind of accounting mass here, light bending there, lensing arcs around galaxies and clusters, telling you quietly that there's more in the cosmic ledger than the visible stars can pay for. Then the story tilted. We turn to information, to the idea that erasing a single bit has a minimum energy cost, as Landauer's principle tells us, tying the faint click of a forgotten bit to heat, to entropy, to the arrow of time. Think about how strange that is, a yes or no choice, written and then wiped away, leaving a physical scar in the form of energy. We let entropy grow, as it always does, and watched it pull information along with it. Black holes became not just hungry mouths, but libraries, their horizons carrying a measure of everything that fell in. The holographic principle whispered that maybe the information in a region of space lives, in some sense, on its boundary. And that is where emergent gravity entered. Space-time in this picture is not a rigid stage, but something woven from microscopic degrees of freedom, with gravity arising the way elasticity arises from atoms in a crystal. In that kind of world, extra gravity around galaxies might not need extra particles. It might be a response to how information is stored and processed. So the speculative idea was this: what you call dark matter could be, in part, the gravitational side effect of the universe remembering itself. Not mystical memory, but physical bookkeeping. The cost of never quite deleting the story of every star, every collision, every quantum event. Here's what we do know, we honestly don't know for certain. Standard dark matter models, with new particles like WIMPs or actions, fit a great deal of precise cosmological data beautifully. The cosmic microwave background, large-scale structure, gravitational lensing statistics, all of it lines up impressively if you assume a dark component that behaves like a cold, invisible fluid. Our information-based picture, by contrast, is still a sketch. No full theory, no complete set of equations. Many ways it could fail when you press it against detailed measurements. And yet something has been gained, a richer sense that energy, information, and space-time might be three faces of one underlying mathematics. A new way of seeing familiar observations, not as a missing substance only, but as a hint that the universe keeps records. For the rest of the journey, you can let the technical details blur at the edges. Let the symbols and numbers soften. Keep only the impression of a universe that is both material and informational, both massive and, in a strictly physical sense, quietly mindful of its own past. Because a very long time ago, before galaxies and clusters and careful measurements, the cosmos began writing a story into itself, and all of it may still be there, pressed into the fabric of space, waiting for you to imagine what it means. So let me tell you a different way to picture where we are. Imagine science as a night walk. You have a lantern in your hand. It throws a soft circle of light on the path, just wide enough that you can see your next few steps, the stones and roots and small surprises right in front of you. Beyond that circle, the world is still there, but it's quiet and dark and full of things you can't quite make out. Here's what we do know. Inside the lantern's glow are the pieces we've tested, measured, argued over, and measured again. Galaxy rotation curves that refuse to slow down the way they should. Light from distant galaxies bending around clusters, tracing invisible halos. Collisions like the bullet cluster, where most of the gravity sails straight through while the visible gas lags behind. All of that sits in the circle. Dark matter itself, though, stands just beyond the edge of the light. You feel its pull in the way stars orbit. You see its fingerprints in the way numbers from observations refuse to match the numbers from ordinary matter. But when you lift the lantern and peer outward, you still don't see a face or a clear shape. Only hints, only the tug on your arm. So people do what they have always done on night walks. They try different paths at the edge of the glow. Some walk down the particle trail, building detectors deep underground, waiting for a tiny flash that would mean a new kind of matter brushing past you. Some turn instead to gravity itself, asking whether the equations we trust are only an approximation, a very good rule that begins to bend on the largest scales. And some of it is going to be even stranger, like the idea that information, memory, and entropy might be part of the missing story. Think about that landscape from above for a moment. Dozens of lanterns scattered through the dark, each lighting up a different patch of ground. No single beam yet wide enough to show the whole shape of the terrain. No guarantee that the most crowded path is the right one. And we honestly don't know for certain which of these small glowing circles will eventually overlap and reveal a clearer picture of the universe. But that not knowing is not a failure. It is the experience. It is like lying under the night sky a very long time ago, before street lights, when someone could look up, see only a few thousand stars, and still feel that something enormous and ordered was waiting to be learned. You are allowed to rest inside that feeling, to notice how much remains mysterious, and how much we have already pulled into the light. Because the next step on this walk may be the strangest one yet. It may be the step where we ask whether the darkness around the lantern isn't matter at all, but the universe's own memory pressing back. And if that is even partly true, then the way we think about space, time, and what it means to forget has to change in a very specific way. So let me tell you, this is the place in the journey where everything can soften. We've walked through rotation curves and bending light, through invisible halos and the strange bookkeeping of information, but underneath all of that there has been one simple picture. A universe that cannot delete its own history for free. A universe that must pay in energy and in structure every time it tries to forget. Think about that for a moment. Every star that ever burned, every collision in a galaxy cluster, every tiny quantum decision a very long time ago and a fraction of a second ago, all of it leaving some faint trace in the fabric of space and time. Not a neat diary written in numbers, but a kind of weight, a pressure, the past pressing back on the present. Here's what we do know. Whatever dark matter turns out to be, it behaves like an extra gravity, a quiet pull that holds galaxies together when, by ordinary mathematics, they ought to fly apart. It shapes the paths of starlight in gravitational lensing. It outlines invisible halos around clusters. It sits there in our equations like someone we can feel in the room but cannot quite see. We honestly don't know for certain whether that someone is a new particle or a new law, or the accumulated cost of the universe trying and failing to erase its own data. Some of it is going to be ordinary physics that we simply have not finished yet. And all of it, whatever the final explanation is, part of the same quiet architecture you live inside every day. So as we begin to wind down, you can let the technical pieces fade into the background. You do not need to remember the names or the principles or which speculative framework went with which idea. You do not need to carry Landau's constants or the details of galaxy rotation any more than you need to recite the recipe for glass to look through a window. Your mind will keep what it needs and let the rest go. You can imagine your own memories doing what the universe's memories do, spreading out, settling, not vanishing, just becoming lighter to hold. Picture them as dust in a beam of light through a dark room, drifting slowly downward, each speck a moment from today or from many years ago, turning in the air and then coming to rest. There was a time earlier in the night when each new idea might have felt sharp and bright. Now, if you like, you can let the edges blur, let the story of dark matter and of cosmic memory become one more gentle pattern your thoughts can move through on their way to sleep. The galaxies will keep turning, the universe will keep its own records. You do not have to. All you have to do is breathe and feel that subtle weight of the day loosening as the light of your attention slowly, quietly goes out. So stay with that for a moment, that feeling of not having to keep track of anything at all. The universe is doing that part for you. While you lie there, there's one quiet thing you can notice. The pull of the earth on your body. your back or your side or the weight of your head on the pillow. That gentle pressure is gravity holding you to this spinning planet, the same basic pull that keeps the moon circling and that keeps whole galaxies from flying apart. It is faint and it is everywhere. Think about how soft it feels here. No drama, no falling, just contact. You're pressed very slightly into the mattress and the mattress presses back. That simple everyday sensation is a tiny echo of the invisible curves in space that guide stars around their centers, and that revealed to our instruments the hidden mass we call dark matter. The same kind of law, the same kind of pull, scaled down until it is just the comfort of lying down. And inside the body that is resting there, there's another story. The atoms in your bones, in your blood, in your brain were made a very long time ago in stars. Some of the hydrogen in you is as old as the beginning, but the heavier stuff, the carbon, the oxygen, the iron, was forged in furnaces that once lit up the young universe. Those stars formed where they did because dark structures, unseen scaffolding, gathered gas into clouds and clouds into galaxies. So someone looking at you now with the right imagination could see layers, a human life, a planet, a galaxy, and underneath that a web of invisible influence, the quiet pattern that helped decide where your atoms would finally come to rest and become you. Here's what we do know. Without that hidden framework, the world around you would not have taken this familiar shape. The bed, the room, the whole history that led to this evening, all of it is balanced on those earlier choices the universe made. If dark matter really is a kind of memory, then you lying there are not outside that memory. You are inside it. You are one of its current entries. A brief conscious pattern in a sea of slower, heavier record. The curve of your spine, the rhythm of your breathing, the thoughts that come and go, all of them are arrangements of matter and energy that the universe is, for a while, keeping. Let me tell you, you do not have to do anything special with that fact. You do not have to feel a certain way, but sometimes when you notice that you are made from star ash, resting on a planet that fell together out of cosmic scaffolding, it is hard not to feel a small, quiet gratitude. Not forced, just a natural softness around the idea that you belong here, that you are woven into the same story as galaxies and clusters and the dark web between them. So we let the language slow down, we let it repeat. You are here, you are held, you are remembered for a time by this universe that cannot quite erase its own history. And as that idea settles, you do not have to follow it. You can let it blur like everything else tonight, as we move from thinking slowly into drifting. So let me tell you, before we close our eyes on this for tonight, what you have actually done. You have walked in your imagination through a universe whose dark spaces are not empty at all, but thick with something we honestly don't know for certain how to name. We called it dark matter. We watched it hold galaxy disks flat, when by ordinary numbers they should have flung their stars away. We watched it bend light around clusters, like a quiet lens made of nothing we can see. You followed that idea further than most people ever do, especially this late at night. You let yourself wonder whether this invisible weight might not be matter in the usual sense, but a kind of memory the universe cannot quite erase. A record of every collision, every orbit, every tiny quantum choice woven into the deep information structure of space and time. Here's what we do know. Information is not just an idea, it has a cost and a weight in the mathematics of physics. Erasing one bit of it, even in a simple computer, releases a minimum amount of heat. So simple, it's almost funny. Think about that the next time you delete a file. Somewhere a few molecules jiggle a little faster because a pattern was wiped away. So some of it is going to be true and some of it will stay story. Maybe dark matter really is made of new particles waiting in quiet detectors underground. Maybe it is a subtle change to gravity. Maybe it is in some distant careful theory, the bookkeeping of cosmic memory. We honestly don't know for certain, and all of it, every version, still tells you the same thing. The universe is not careless with what happens inside it. And that means you do not have to hold everything in your own mind tonight. You have done enough. You have walked through galaxies and equations and very large stretches of time. You have let your attention circle ideas the way stars circle a halo they cannot see. That is plenty for one small human evening now you can let go. The universe will go on remembering and evolving without your effort. Galaxies will keep turning. Light will keep curving. The quiet weight of whatever dark matter is will go on shaping the world, whether you're awake to notice it or not. Sleep, for you, is a tiny version of that, letting go, a way of handing the story back to the larger pattern that has been running since a very long time ago. So we come back to the dark and the stars and the quiet weight of memory. The dark, the stars, the quiet weight of memory, each repetition a little softer, a little farther away as you drift toward the edge of waking. Because there's one more place this idea can take you if you follow it, and it begins with asking what else the universe might be remembering right now in you. If you're still here and not quite all the way asleep, let me tell you a small secret about tonight's story. You don't need to remember any of it, not the names, not the numbers, not the diagrams. Your mind tried to sketch in the dark. The universe will go on turning without you recalling a single detail about dark matter or information or space-time. And that is perfectly fine. What stays with you, if anything stays at all, can be much smaller than the whole idea. Just one question. A quiet one you can carry with you into tomorrow, like a smooth stone in your pocket. Something as simple as how much of my world is built from things I cannot see. Think about the day waiting for you on the other side of sleep. You wake up, you reach for your phone, and messages are already there from someone who is not in the room. No visible thread connects you, only invisible networks, radio waves, codes, and agreements between distant machines all humming away in the background. You step outside, a door unlocks because a tiny pattern in a piece of plastic tells it to. Traffic lights change because an unseen timing system is counting down. Money moves between banks because numbers in distant computers rearrange themselves. None of this is visible in the way a tree or a cup of tea is visible, and all of it shapes your experience. Here's what we do know about those systems. Underneath the surfaces you can touch, there are layers of memory and structure, all quietly insisting that things stay in a certain order. Passwords remembered, locations stored, histories logged. Every app, every website, every GPS route is a little architecture of invisible information holding the day together. If you like, you can treat each one as a tiny reflection of the larger architectures we've been wandering through. A navigation app leaning on satellite signals and geometry. Streaming video leaning on compression algorithms and long chains of mathematics. A power grid leaning on fields you never see, small echoes of dark matter, halos, quantum events, and the deep memory of space-time. We honestly don't know for certain how far that analogy really goes. Some of it is going to be just a helpful picture, nothing more. But as you notice these hidden structures, you might feel a faint family resemblance between the invisible scaffolding of your day and the invisible scaffolding of the cosmos. And if that feeling interests you even a little, that's where you can always come back here on another night. The same story will be waiting, but you will not be quite the same person. Different parts will stand out as your own memories and questions quietly rearrange what you hear. Or you may forget all of this the moment you close your eyes. That is also a good outcome. Either way, the universe will keep on remembering for both of us. And if tomorrow or some other night a little fragment of this idea drifts back to you, that can be the beginning of a new, very gentle conversation you have with the world. Not a loud one, not an urgent one, just you and a question and a bit of time. When you're awake and the day feels wide enough, you might feel like following one of those questions a little further. You might pick up a book about galaxies or dark matter or the strange way information and entropy are tied together. You might watch another slow video that walks through how someone measured the rotation of a galaxy and realized there was something missing. Or you might simply look up on a clear evening and notice how the sky is not empty at all. Think about every star you can see and all the ones you cannot, sitting in those invisible halos whose gravity we traced from bending light and drifting gas. You do not have to remember the names or the numbers for that to matter. The experience itself is enough. If this way of telling stories felt comfortable to you, if the slow pacing and the speculative edges and the long winding sentences made it easier to breathe, then let me tell you, you're allowed to seek out more of that. Some of it is going to be about mathematics, some of it about physics, some of it about memories that began a very long time ago, before there were people to name them. And all of it can be a quiet place you return to when you want wonder without hurry. Here's what we do know. You do not need to do anything right now. You do not need to tap or click or decide. If on another evening you feel like coming back to this channel or subscribing, so these long, slow stories are easier to find, you can treat that as a way of keeping a small corner of your life reserved for unhurried thought. A shelf in your week where the universe is allowed to be mysterious and you are allowed not to solve it. There's no rush. The galaxies that reveal dark matter have been circling for billions of years. The information written into the fabric of space has been accumulating since the first light broke free. Your curiosity can unfold just as slowly, with the same patience. So for now, I wish you deep rest and vivid dreams, and a gentle sense that you belong in this universe that remembers. May whatever you forget tonight be held for you somewhere in that vast, quiet memory until you are ready to ask again.